Hey guys, Miss Peterson here, and this is AP Physics 2, Lecture 1-3, all about Bernoulli's principle. We're going to get away from static fluids and be talking about dynamic fluids, how they move, the continuity equation, and Bernoulli's principle. So, how do fluids flow? Okay, well, they flow through the pipe. And the way that we measure that is typically through something called the volume flow rate, where the volume flow rate is just the volume of fluid that flows past a point every second, okay? And we find that with A times V. Its standard units are meters cubed, okay? Cubic meters, unit of volume, per second, okay? The volume per second, volume over time. Now, the volume of water at any point in the pipe must be equal entering and leaving, okay? That's always going to be true because if not, we would get a clog, the pipe would burst, and hopefully that doesn't happen. Does it? Yes, but that'd be a whole different set of equations. So for a pipe that is put together and the volume of water entering equals the volume of water leaving for any point, we can write the principle of continuity. And this is the way this equation is on your equation sheet. A1 V1 equals A2 V2, okay? Where A is the surface area of that cross-sectional area. Let's actually do cross-sectional area. That's a better word for that. Normally in units of meters squared, and then V is, of course, the velocity of the water, normally in meters per second, so that's where we get the volume from it. And we know this equation intuitively, okay? If I'm watering my lawn and I want the water to go farther, if I want it to come out faster, I put my finger over the nozzle. Why? Because when that pipe narrows, that flow must speed up, okay? If that area goes down, the water must speed up. If it didn't, we would have too much volume trying to get through that area and it would get clogged, okay? So yeah, anytime you need to think about this, just think of putting your finger over the hose. Okay, cool. Okay, cool. So what is Bernoulli's principle? All Bernoulli's principle is a statement of conservation of energy within a fluid. You might remember from AP Physics 1 or other previous physics classes when you would do conservation of energy problems. You would have the kinetic energy plus the potential energy equals the kinetic energy plus the potential energy. We could throw in other types of energy in there as well. And that's kind of what Bernoulli's principle is, except for pressure and fluids. So it is the longest equation on your equation sheet, and it is P1, capital P, plus rho Gy1 plus 1/2 rho V1 squared, okay, equals P2 plus rho Gy2 plus 1/2 rho V2 squared. It even kind of looks like a conservation of energy problem, okay? And we kind of call it that. This term right here, the P1, or the P, that is called your gauge pressure, okay? And that is just the pressure due to it like being a fluid, whatever that pressure is at, normally measured relative to the atmosphere. And its units are going to be pascals. And remembering that a pascal is a Newton per meter squared, okay? Now, this term in the middle, okay, that one we call the, hydrostatic pressure, okay? That's the rho Gy term. Now, in this equation, this y, okay, refers to the height, okay? Not necessarily the depth. I know in our previous lectures we were using h for the depth of the water. This is still related, but now it is y and it is for height. Why? I don't know. That's just how the equation sheet does it, and that's how AP Physics curriculum does it, so that's how I'm going to do it. Now, if we look at the terms for this hydrostatic pressure one, we have density, which is normally going to be in kilograms per meters cubed, times, oh, this is over here. I'm just doing the unit analysis. Okay, now I'm doing the unit analysis as a sort of derivation of this problem, just kind of making sense of where all of these terms come from. Because this equation is so big, I often won't put units in when I do the math during this problems, but I promise it'll be okay. And yeah, the derivation of it actually isn't found in most textbooks. And you do not need to know how to derive it, but if you want to, there's a lot of great teachers on YouTube who have derived it. And I will link one of those posts. So then back to the notes, we have G, which is meters per second squared, and then a height, which is normally in meters. So if we cancel this out, we have two m's, make that just m to the first, and we're left with units of kilogram meter per second squared, which at first glance doesn't really look like a Newton meter squared. But if we remember that a Newton is a force unit, so it is mass times acceleration units, kilogram meter per second squared. And then let's look at this and plug that in there. We'll have kilogram meter per second squared over meter squared. So then what ends up happening is we have the meters squared canceling out with that meters. So this does simplify down to kilogram meter per second squared, which is the same as the units of that, which is good because we can't add terms unless they have the same units. And then the last pressure is the dynamic pressure. This also, I want to note, is kind of just P naught plus rho G H. Okay, this is just an extension of that pressure formula, but now including dynamic pressure, the pressure due to that movement. And that term is the 1/2 rho times that velocity squared. And again, we can look at the units just to make sure that they'll always work out for us. 1/2 doesn't have units, and then we have kilograms per cubic meter times meter per second squared, so meter squared per second squared. And we can see that that same kilogram over meters per second squared pops out, aka a Newton meter, aka a Pascal. A little messy, but okay, cool. Okay, cool. So let's go ahead and look at the effects of this. Okay, starting with just if the height changes. So in this one, they're saying that V1 here is equal to V2 there. And what will happen to the pressure at point 2 compared to the pressure at point 1? Well, two different ways you can look at this. If we looked at this with those velocities being equal and we were just thinking about that hydrostatic pressure, okay, that rho Gy, well, this one is up higher. And we know things have higher pressure when they are lower. So at P2, the pressure is going to increase, okay, because it's deeper in the fluid, okay? So the pressure will increase. And if we looked at that through Bernoulli's, okay, P1 plus rho Gy1 plus 1/2 rho V1 squared equals P2 plus rho Gy2 plus 1/2 rho V2 squared. Now they're telling us that those velocities are equal. So these two terms would subtract out, okay, because they're going to be equal. So if this is our starting one, and then our height, okay, H2 is less than height 1. So this term would decrease, which would cause the pressure to increase. Okay, cool. Okay, cool. But what if the area changed? Okay, so now we're looking at that second picture. Now we're looking at this pipe. So a pipe that has a large cross-sectional area to a small cross-sectional area. And note the midpoint of the pipe is all at the same height, and that's what we typically go with as our height measurement. So that is one where the height's going to be constant. So what's going to happen to the pressure? Well, Bernoulli's does not have a term for the area in it. Okay? So whenever we're doing things with area changes, we have to start from the continuity equation. A1V1 equals A2V2. Now, if we're going from, I'll say this is my spot 1 and this is my spot 2 and 2. So if we're going from spot 1 to spot 2, the area is decreasing. So if the area is decreasing, the velocity must increase. So the velocity increases. And so looking at Bernoulli, these two terms would cancel out because they would be the same. Okay. And then we're saying that the velocity is increasing. So this term is going to increase. What's that going to do with the pressure? It's going to decrease. The pressure will decrease. And that's what you see in this picture, how that water level isn't rising to as much, okay? Because the pressure is less in that area of the pipe. Okay. Now, when we're using Bernoulli's, it is helpful to remember that it only applies to ideal fluid flow. So ideal fluids are incompressible, which is definitely more true, this should say for gases than liquids. Definitely more true for gases than liquids. Oh, sorry. Nope, it was right. It is incompressible. More true for liquids than gases. If we have a syringe with air in it and we squish it, we can squish it. If we have a syringe with water in it and we try to squish it, the water's going to shoot out. Now, viscosity is a fluid's resistance to flow. It's how much it sticks to surfaces and sticks to itself. We ignore that. And we assume that it is streamline or laminar flow and all of the water molecules are moving in the same direction. So it's a bit of a simplification, but it's a lot like ignoring friction and air resistance in that it works for us most of the time, but every now and then, not so much. So let's go ahead and look at an example problem. Okay. In a town's water system, pressure gauges in the still water at street level read 150 kPa. If a pipe connected to the town system breaks and shoots water straight up, how high above the street level does the water shoot? Okay, so let's talk and set up what we have going on here. We have a pipe, okay, and it's at street level, so we'll just say height of the pipe equals 0. And then in still water, so when V equals 0, the pressure is 150 kPa. Okay. But then the pipe breaks and shoots water straight up. Okay. Now, there's two different ways that we could kind of tackle this. We can consider point A to be right at the bottom of the pipe in the still water, okay, before it is shot up, and point B to be at that top of the stream of water. Is it still in the pipe? Technically, no, but that is part of its exit. Another option is to use the still water over here and find the flow velocity, okay, the velocity at which water will exit that point, and then use kinematics to calculate how high it'll go. But since we're in Bernoulli's, I'm going to go ahead and try it using Bernoulli's. So I'm going to put my point 1 down there and my point 2 up here. So we want to know how high above street level that water goes. Okay, so let's see. We have P1 plus rho gy1 plus 1/2 rho v1 squared equals P2 plus rho gy2 plus 1/2 of rho v1 squared. Okay. Now, we know that it's at still water to start with, so I'm going to set that y as 0. Anything times 0 is 0. And then it is still water. It's not moving. So at that point, its velocity is also 0. Okay? So our pressure at that street level is 150 kPa. Now, that's going to equal this pressure as we go up. Now, this is can be a little bit confusing because there are two kind of ways we can look at this. This P1 is 150, but it is the pressure gauge, okay? It does not consider the atmospheric pressure. Now, for our point 2 is not in the pipe anymore. It is in the atmosphere. So that is a gauge pressure of 0, okay? That's it. It's a gauge pressure of 0 because it is no longer in the pipe. If we had a pressure gauge just in the atmosphere, it would read that pressure of 0, not the 100 kPa. Yes. Okay, so P2 will be 0 because it's open to the atmosphere. And then we're trying to solve for that y. And for the velocity of it, what is that velocity going to be of the water at its max height? It's going to be 0, okay? The water, before it goes up, it has to come back down, just like a ball or anything that we did in kinematics of AP Physics 1. So this velocity would be 0, meaning this term would also be 0. So we have 150 kPa equals the density. It's water, so 1,000 kilograms per meter squared. And because I know this will be in units of pascals, I'm going to change this to 150,000 pascals, or 1.5 times 10 to the 5th. So we have 1,000 times 9.8 meters per second squared times y2. And so when we do that, we get that it goes a vertical distance of 15.3 meters. Okay, cool. Okay, cool. We'd probably just say about 15. Let's look at another one. A fluid with a density of 1,250 kilograms per cubic meter has a pressure of 45,000 pascals as it flows at a velocity of 1.5 meters per second through a pipe. Okay, so that's our P1 and our V1. The pipe then rises to a height of 2.5 meters. Okay, so Y2 is 2.5 meters, where it connects to a second smaller pipe. Okay, what is the pressure in the smaller pipe if the fluid flows at a rate of 3.4 meters per second through it? Okay, so we have a small pipe, and then it's going to, or a bigger pipe, and it's going to a smaller pipe as it goes up. Let's go ahead and set up our problem. we have P1 plus rho GY1 plus 1/2 rho V1 squared equals P2 plus rho GY2 plus 1/2 of rho V2 squared. And our initial height, we're going to set as that 0. And then our final height is that 2.5. Okay. We know our initial velocity. We know our final velocity. This is the term that we're looking for. Okay. Yeah, I think we're ready to just plug in our numbers. So we have P1 is 45,000 plus 1/2 of 1250 times 1.5 squared equals P2 plus 1250 times 9.8 times 2.5 plus 1/2 times 1250 times 3.4 squared. And now you see why sometimes I don't put units in while we write Bernoulli's, because that would be a lot to write. So now we just have to math it out. And we have 46,406.25 equals P2 plus plus 337,850. So we get a P2 of 8,556. I'm going to round it and just say 8,560 pascals. Or you could say 8.6 kilopascals. Yep. Okay, cool. Okay, cool. Now, often in these problems, we are going to use Torricelli's theorem. Torricelli's theorem is a special application of Bernoulli's principle that we use to solve for an outflow velocity of a large tank of water. So we're going to have our point 1 up there and our point 2 down here open to the atmosphere. So when we use Bernoulli's principle with this one, okay, well, point 2, we can set our initial height as wherever we want. So normally we set point 2 at, So we'll start from that basics. Now, when we're doing these outflow velocities, normally we have open tanks of water. So both point 1 and point 2 are open to the atmosphere. So they'd be at a gauge pressure of 0 or just atmospheric pressure, depending on how you want to look at it. So we can go ahead and ignore these two terms. Okay. And then, because at this point that is going to be moving down so much slower than at the outflow velocity, we say that V1 is so much smaller than V2 that it's basically 0. Okay, and so we ignore that velocity V2. Sometimes this is just because it's such a large tank of water that it's basically not moving at the top, or sometimes in the problem it'll tell you that they're matching the leakage, that they're refilling the tank, things like that. Okay, so now our equation simplifies and becomes rho GY1 equals rho GY2 plus 1/2 of rho V2 squared. So we can cancel out the rho from each of the terms, and then I'm going to start combining like terms. So I have GY1 minus GY2. I'm trying to isolate the v, so I'm going to move the 2 over as well. So I have 2 times gy1 minus gy2 equals v2 squared. Okay. I'm going to go ahead and factor out that g. So 2g times y1 minus y2, and then it'd be the square root of it equals that outflow velocity. Okay. Now, wait, if we're just talking if y1 is height 1 and y2 is height 2, then the depth of it, okay, which we use an h for, is just y1 minus y2. So we can rewrite that as square root of 2gh equals v2. Now this is Torricelli's theorem. And it can be applied to any water tank / like outflow, where V2 is going to be much, much faster than V1, okay? Where V1 is so small that it's almost negligible. Then we can solve for that outflow velocity just using the simplified equation of the square root of 2gh. So let's go ahead and do that as an example problem. The side of an above ground pool is punctured and water gushes through the hole. Okay, big pool, little hole. If the total depth of the pool is 2.5 meters, okay, and the puncture is 1 meter above ground level, okay, so I should probably draw a better picture there. And then the thing is 1 meter above ground level, okay. What is the efflux speed or the outflow speed of the water? So Torricelli's applies. Okay, the outflow at V2 will be much, much greater than the speed going down in the pool. So we can use velocity is the square root of 2 times 9.8. And then remember, h is the depth. So what is the depth here? y2 minus y1, 2.5 minus 1. It would just be that 1.5 meters. Now I can put units in this one. Okay, so we get a velocity of 5.4 meters per second. Okay, cool. Okay, cool. Now, let's go ahead and look at some demos. Okay, so we're going to go ahead and start with the blowing cans together demo. Here, I have 2 empty soda cans right here in front of me, okay? And I'm going to get them pretty close, but not touching. And then I'm going to blow air in between them. And your first instinct might be to think that they are going to go apart. Okay, if I blow at them, they should go apart. But let's see if that's what happens. Okay, see if we can see it again. They move together. Okay, what happens is when I speed up the air in between them, get them to slam together. Okay, when I speed up the air in between them, the air pressure between the 2 cans gets lower. Now, sometimes we think this is counterintuitive. Why would the air pressure be lower? Okay, and then this outside air pressure pushes them in. Well, pressure is just due to that random motion of molecules. So if in between the 2 cans, all of the molecules are moving in one direction, they're going to be less likely to hit the sides of the can because they're all going to be going through them. And that's why that moving air causes lower air pressure. Now, can you use that principle to explain what's going to happen when I blow over this piece of paper? Okay. Very similar idea. The faster moving air on top lifts the paper. Okay, and you can even do this to levitate a ping pong ball. So I have a blow dryer here. It's going to create a stream of air with lower pressure. So when I put this ball there, it will stay in that stream of lower air pressure. Okay? Pretty cool. Okay, cool. Okay, cool.